All right, so what we're going to start to do is move towards graphing functions and identifying the behaviors of the functions from their graphs. So this is going to be the first set of notes that you need to complete on your own at home. What we're going to do is we're going to go through about half of it in this video, and then tomorrow when we come in, we'll complete the back portion and we'll start practicing some of those skills. So a lot of this should be review, and you should be able to do this first task here, which says to sketch the graph of y equals 11 minus 3x. And I know that a lot of you right now are probably already recognizing that this is a linear function. This is linear. And it's obviously linear because lines are of the form y equals mx plus b. And even though this thing isn't quite set up the same way as the standard form of a line, we can see that if we rearrange these two components, we'll end up with negative 3x plus 11. So then we will have our y equals mx plus b form, right? This is your m, or your slope, and this is your b, or your y-intercept. So we could graph it just knowing what we know about lines. But if we didn't know that it was a line and we didn't know what type of function this was, we would always have a tool that would be useful to us for graphing any function. So what we would do is we would just make a table, something that you should get in the habit of doing if you're not sure what this function is going to look like, and just pick a number. I think there are some easy numbers to plug in for x, and then we will have some outputs as well. So one number that I might plug in for x would be 0. It's an easy one to start with. Well, if x is 0, then we're going to have negative 3 times 0, which is just going to leave us with 11. So in the event that x is 0, y is 11. And we're just going to keep going through and we're going to plug in some more numbers. If x is 1, well then it's 11 minus 3. So if x is 1, then y is 8. And if x is 2, then it's 11 minus 6. So we're dealing with when x is 2, then y is 5. And we could keep completing this table like this. What we're going to do now is we're going to move the other direction. So we're going to say, well, what would happen if x was negative 1? Well, if x was negative 1, then this would be negative 3 times negative 1, which would be positive 3. So we would have 11 plus 3 instead. So we would end up with a y value of 14. And if x was negative 2, well, then we would have a y value of 17. All right, so now we have kind of an idea of what this function is going to look like. We could continue on in both directions. I could keep going extremely positive or extremely negative. Either direction wouldn't really make a difference. But what I want to do now is just kind of sketch this function. So let's just roughly sketch our linear function. You should try to be careful about the way you label your axes. It looks like on our y-axis we're going to need to include some higher numbers. So maybe we'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That maybe is a good way to go. 2, 4, 6, 8, 10. Looks like we won't have to go too far in the negative y direction. In the x direction, though, I'm going to count by ones. And let me just show that I'm counting by 2s here. But in the x direction, I'm going to go 1, 2, 3, 4, 5. And negative 1, negative 2, negative 3, negative 4, negative 5. This does not have to be perfect. We're just sketching. All right, so let's start plotting this function. We've got a bunch of points here. We've got 0, 11, which is at 2, 4, 6, 8, 10 right here. All right, so that's the point 0, 11. 1, 8, which is here. 2, 5, which is about there. All right, so we're starting to see what this function looks like. I can put in the other two that we graphed. Negative 1, 14, 2, 4, 6, 8, 10, 12, 14. All right, so it's about here. We've got another one. It's about here. All right, so this line just right now looks like what we've graphed. And we could fill this in and say that this continues forever and ever in both directions, because we know that just because we only plotted these 5 points, that doesn't mean that we couldn't have continued to plot more. So the next thing that we're going to start to do is we're going to start to look at these graphs, and we're going to determine x and y intercepts of our functions. And what I want to do here is observe the behavior of these functions in order to figure out what those intercepts will be. We know probably that the y-intercept of this function is 11, right? You know that probably because this is the point 0, 11, and because the function is crossing the y-axis right there at that point. So your y-intercept is wherever your function crosses the y-axis. Let's define that over here. All right, so we should probably define that. And in this case, that's at the point 0, 11. Now, there is something that you'll always notice about the y-intercept. Anytime we have a y-intercept, the x-coordinate of that y-intercept will always be 0, because if you're sitting on the y-axis, you are at 0 on the x-axis. So that's an important thing to note. All of our y-intercepts will always have 0 as an x-coordinate. X-coordinate will always be 0. So what we want to look at now is we want to look at our x-intercepts. And we do have another word for x-intercepts. We call our x-intercepts roots or solutions or zeros. So let's define x-intercept very similarly here. And let's remember that when we're on the x-axis, our y-coordinates must be 0. All right, so we can see that the y-intercept of this function is 11. So when we get to this point here where we're trying to figure out, well, based on the function above, what is the y-intercept of this function? Well, I know that the y-intercept is at y equals 11. I know that because I can see it there. But how could we have done this algebraically? Well, what we would do is we would have to use this information. If I ever want to find the y-intercept of a function algebraically, all I have to do is just make the x value be 0, and it will tell me what the y value of my function is. So if I start to figure this out algebraically, and I have my function y equals 11 minus 3x, and I want to figure out what is the value of y when x is 0, I'm just going to replace x with 0. So y equals 11 minus 3, let's make x 0. And in this case, of course, we get 11. So following that same logic, if I want to find the x-intercept, I could just switch this process around. And if I want to know where my function is going to cross the x-axis, I'm kind of wondering here, well, what I've got to do is make my y-coordinate 0 and see what happens. So my function is y equals 11 minus 3x. And if I want to find the x-intercepts, or the roots, I'm just going to make my y-coordinate be 0. And now I have to solve for x. So I'm going to move my 11 to the other side. Negative 11 equals negative 3x. And to get x alone, I'm going to divide by negative 3. So I'm going to have 11 thirds. All right, so my x-intercept, and I should make these arrows, is x equals 11 thirds. So you can see now why this was starting to trend towards a point where it may not have been a whole number. Now we know for sure that it wouldn't have been a whole number. But we know now that this function would have crossed the x-axis right at 11 thirds, and we're able to find that algebraically. All right, and that's what we're going to be doing moving forward, is using the graph less and using the algebra more. And this finding of intercepts is not something that's new, but we need to make sure that we define it pretty clearly. The last thing we're going to do here is sketch and evaluate this function, and just so that this video doesn't go too long, what I want to do first is just kind of sketch this thing so that you see what it looks like, and then I'll talk a little bit about it and we'll touch upon it in class. So what this is an absolute value function. So absolute value symbols look like this. And then there's something inside there. And basically what we're doing here is we are just measuring the distance that this expression in here is from 0 at all times. And you've seen it before, but what you need to know is that this cannot be negative. So for example, if I were to take the absolute value of 4, I'm just asking how far is 4 from 0? Well, the absolute value of 4 is 4. It's 4 units away from 0. What's the absolute value of negative 3? Well, how far is negative 3 from 0? It's 3 units away from 0, so the absolute value of negative 3 is 3. All right, so this output of this function will always be a positive value, because when we measure absolute value, we can't get a negative result from that. So what we're going to do is we're just going to sketch this thing out, and I'll just show you what it looks like from making the table. All right, so I would encourage you to write this down as well and probably go back and study where some of these points came from, because I don't want this video to get too long on us. But what I've done is I've just plugged in my x value a bunch of different times into f of x, and this is my output. Remember, f of x, we could call it y, we could call it g of x, we could call it q, whatever. This is just like our y value here. So when I plugged in a -5, I ended up with -5 plus 2. -5 plus 2 is -3. And we just outlined over here that the absolute value of -3 is 3. So when I plug in a -5, my output is going to be 3. All right, and I plugged in a -4, same thing. I got -2, but the absolute value of -2 is +2. And I plotted all these out until I ended up plugging in a -2 and getting 0. 0 is 0 units away from 0, so our output was 0. And then we started plugging in values to the right of this point and going back up again. This is what an absolute value function looks like. It will have a point that it ends up bouncing off of and going backwards in the other direction. So I'd encourage you to take a look at it, and before you come in tomorrow, I want you to tell me what the x and y intercepts of this function are. Just make a note of them on your page. Say the x-intercept is, and the y-intercept is, and you shouldn't need to use a whole lot of algebra here because they're visible on the graph and in the table. But make sure that you understand where this function comes from. We're going to play around with a couple different types of functions when you come into class tomorrow.